So today we're going to start talking about covalent bonds. And this is the other kind of bond. Before we had ionic bonds. Ionic bonds took place between metals and nonmetals. And generally because their electronegativities are great enough for the nonmetal. I'm sorry, the electronegativity difference is great enough. Electronegativity, I need to erase that, sorry. Electronegativity the electronegativity differences are great enough for the nonmetal to take valence electrons from the metal. All right. So what happens when we can't? What happens when you have electronegativity differences that are small? And the way that happens is if you have two nonmetals together, and normally they would just make negative charges if they can gain electrons from the metals. Well, if we have nonmetals and nonmetals, so if you have nonmetal bonds, what do they do? Okay. Yes, they share. They share electrons. Oh. Okay. So how do they share? That's what the word covalent means. Covalent. Okay. Okay, if you're cooperating with someone, if you are cohabitating with someone, or if you're covalent, co means both. Okay. And in this case, valent is referring to, what do you think? The valence, right. So both valence. Okay, or both valences. All right. That electrons that they share are going to exist in the valence shells of both atoms between a covalent bond. Okay, they get to count for both of them. You guys follow me there? Okay, so the basic one that we're going to do, we're going to start with fluorine. Fluorine and fluorine. So we're going to do our dot structures of fluorine. I'm going to suggest to you that you draw them like this, and then draw the other 7, just for illustration purposes. All right. How many electrons does fluorine need? It needs 1. It's got this spot right here to fill before it's happy, before it has its electron configuration, its noble gas configuration. Yeah? Same thing for this one. It's got this one that it needs to fill. Well, if they decide, I'm personifying them, they don't actually decide. Remember, it's the energy thing. But what happens is that these two electrons can fulfill the electron configuration of the other one if they're shared with each other. So if these two electrons count for both, you wind up with these two electrons working for both of them. okay, that these two electrons become covalent. That they get shared so that this fluorine has all 8 electrons. And that fluorine has all 8 electrons because these 2 electrons in the middle, draw that neater. Okay, they are a shared pair of electrons, also known as okay, this is a covalent bond. Yeah? Good there? Okay. There's 2 branches we can take from here. Where did my... Okay, we can go this direction, where we have okay, so we can go 2 directions from here. We can go to where we're sharing multiple electrons between 2 atoms, or we go where we have more than one atom sharing to the same atom. All right. So next one I'm going to show you guys is okay. So I got to move here. Okay. Here's oxygen. In fact, I'm going to start, at this point, I'm going to start using these standard colors for our atoms. Oxygen is usually in red. Does that show up red for you guys? Reddish. All right, let's make a little. Red doesn't show up really well on a dark background, so let's see if I can. Yeah. Okay. So what are our electrons like for oxygen? Oxygen's going to have. Oxygen has 6, right? Okay, and we are going to hook it up with fluorine, and usually we do halogens as green. Okay, fluorine has a spot right here that it wants to that it needs to gain an electron from somewhere else. Yeah. Well, oxygen has 2 of them. Yeah? It's got one here, and it's got one here. Remember when we were doing our ionic bonding, and we said that we're not doing these as an atom-by-atom thing. We're not taking our little tweezers, our atomic-sized tweezers, and piecing them together. That when these reactions happen, there's plenty of atoms of both of them everywhere. Yeah? Which means we have enough fluorine and enough oxygen to do whatever we want within however many quantities we need. Yeah? Well, if fluorine needs 1 space, oxygen has 2. Oxygen can actually give up 2, it can share 2 electrons, right? This one and that one? And then the fluorine can share 1, so oxygen needs another partner, right? So couldn't it bond with another fluorine? And so these guys share in these spots. Yeah. And so what would we have? We would have an oxygen. Okay. And all of a sudden we have an oxygen with all of its 8 electrons. We have fluorine with all 8 that it wants, and this fluorine with all 8 that it wants. And this would be, we would write this as, this would be O, F2. Okay, and this would have the name of, check this out, oxygen difluoride. And this is new. In nonmetals, in covalent compounds, we start using these Greek prefixes. What's that? Di, difluoride. Oxygen difluoride. You've heard of something like this before. Okay, and there's a very common one, and that's what we're going to do next. Okay, so we have multiple atoms sharing, so we can, more than one atom can come in and fulfill our sharing stuff, so that we're going to get a, so we get this 8 right here, and we get this 8 right here, and we get this 8 right here, and everybody's happy, and everybody has their 8 electrons. Okay. The other version is this one, multiple electron shares. Okay, you guys don't need to erase, I'm just doing it to get rid of space. Okay, sometimes we're going to start with oxygen again. Oxygen, it's got 1, 2, 3, 4, 5, 6, and it comes across another oxygen that is 1, 2, 3, 4, 5, 6. Okay. This oxygen needs to share 2, right? With someone? Well, so does that one, right? Both oxygens need to share how many? 2. So they do. They share 2 pairs of electrons. That these 2 are going to share with each other, and these 2 are going to share with each other, and we get O. These 2 electrons, these 2 pairs aren't sharing. We're happy. Those 2 pairs are happy. Okay, but in fact, this is called a. Both of these guys are called lone pairs. Lone pairs. Lone wolf. Lone pairs. Okay. In other words, they stand by themselves. They don't need to share with anything. You have this pair of electrons that's in its own little orbital by itself. These get shared, and so these guys are in a little orbital, and these guys are in a shared orbital. Okay. But if you look at if they're going to be happy or not, this oxygen has all 8 of those. This oxygen has all of those, and it has its octet, right? It has its 8 electrons. Okay? This is how covalent bonding works. All right, and this would be, okay, this is actually just oxygen. This is how oxygen occurs in nature, is in this bonded, and the formula for it is O2. Ah, good question. What about carbon? We'll get to that right now. That was a perfectly timed question, Mr. Tanner. Okay, I've got to kind of... Carbon is usually black. Black does not show up well on black. So I'm using a gray. Why did you ask about carbon, Tanner? Right, it's got 4 valence electrons. Well, I'll tell you right now, it's not going to be able to share all 4 electrons. That is too high of an energy state for it to have. The electrons don't like each other, right? And if you're going to throw all of them into the same space like this, right, to bond with each other, there's too much repellent force between them for that to work. But that's actually really cool about carbons. Because of that purpose, they will always have this one extra electron hanging out. Yes, yeah, thank you. Okay, we'll get to that in a sec. The one I want you guys to look at right now is we're going to make carbon dioxide. Okay, you guys should know the formula for carbon dioxide. What does that di mean? 2. Oh. Right? So that's this di means 2. You guys have heard of this before. It's carbon dioxide. But here's how it works. Let's see if we can you guys see that carbon? That's okay. All right. This carbon has 1, 2, 3, 4 electrons around it. Oxygen. Each oxygen has how many? Each one has 6. And I'm going to draw them on opposite sides for strategic purposes. Okay. Oh, by the way, notice how I drew the carbon wrong? Right, so your first two are supposed to go together? Well, when we're doing covalent bonds, we're trying to figure out how they bond with each other. We draw them separately so we can show that each electron is going to do its own thing. How many spots does carbon have to bond? 1, 2, 3, 4, right? How many spots does oxygen have to bond? 2 and 2, right? So this one has 2, this one has 4, this one has 2. What do you think is going to happen here? 2 of these are going to come over here. And 2 of these are going to come over here. Yeah? You guys see this? And let's finish those up. So, our oxygen too far. It's going to look like that. Now, I'm color coding them on purpose because I want you guys to be able to keep track of That oxygen has 8, right? That oxygen has 8. How about this carbon? It's got 8. Okay. We've seen this phenomenon twice now. We've got that, and we've got that, and that, where two atoms are sharing 2 pairs of electrons, right? This carbon and this oxygen are both sharing 2 pairs of electrons. Here we have another 2 pairs being shared. Yeah? Okay. This is called a double covalent bond. And over here, this is a covalent bond. And so, Tanner, I hear the question. Ask the question, man. That wasn't the question I was hoping for. But that's okay. Can we make 3? Yes, we can. Okay, so we can make 3, and we're going to use... We use kind of a teal, by the way, for nitrogen. Nitrogen is light blue or teal. Nitrogen is going to have 1, 2, 3, 4, 5 electrons, right? Yeah? If I say so? It's not about if I say so. It's... Okay. Then we have another nitrogen that's going to be... In fact, I'm going to replace this one. That's your mistake. Although I do tell you guys right in pen. Oh well, sorry. It happens. Okay, I moved it from here over to the side because I want to get the pairing electrons close to each other to illustrate. Okay, well, look at that. Nitrogen has 1, 2, 3 spots. This nitrogen has 1, 2, 3 spots. Well, what do you think they're going to do? They're going to bind, and they're going to make... Okay, you will sometimes also see this as... and the reason you would see it like this is because it's easier to type colons. Right? N, colon, colon, colon. Like shift, semicolon. Right? On your typewriter, so you don't have to do extra special graphics. But I like drawing it like this because it illustrates what we're trying to do. And there's this 8. And there's this 8, and this would be N2. This is the normal form for nitrogen. Nitrogen occurs in nature as N2. Okay, it is a... This is a diatomic molecule. There are 7 of them. In fact, I need you guys... You're going to write these down right now. You need to know what these are. Okay, they are the magnificent, I call them Magnificent 7. This is my term for them. There are 7 of these. And it's because they make a 7 on the periodic table. So the first one is hydrogen. The hydrogen actually is not in the physical 7 on the periodic table. But the ones that are start with nitrogen, they go to fluorine, and they go down to iodine. Okay, and there's another 6 there. So hydrogen, the one up there, then N2, O2, F2, and then we turn Cl2, Br2, and I2. Okay, so it's these. I'm trying to talk loud enough to get into my mic. Hydrogen, and then here's the 7. You guys see it? It actually makes a 7 on the periodic table. So there's 7 elements, and the other 6 is hydrogen and the other 6, right? But the other 6 make a 7 on the periodic table. What's that? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. But look at if you look at the periodic table, they're here, and they make a 7. Right? That's why I call it magnificent 7, because they make a 7 on the periodic table. They're in the shape of a 7. All right, you have to know these. Memorize them. No, you need to know if you see chlorine. If I say when we start getting the reactions and stuff, if something reacts with chlorine, it's Cl2. If something reacts with oxygen, it's O2. Every freaking time. These are the elemental forms. These are the diatomic elements. Okay, if we name this element, they come in pairs. And all of these are covalently bonded. That one's got 3, that one's got 2. The other ones have singles. Okay. Cool thing about carbon, finally. Okay, carbon bonding. Can you guys all see that? Okay, I know it's getting kind of dark. Okay, carbon bonding. Carbon has these 4 electrons. The most that you can bind, the biggest covalent bond that you can have with another atom is a triple covalent bond. Yeah, here's this one's the triple, by the way. Well, with carbon can do that to get, but that still leaves this extra one out here. And this is this property of carbon is the foundation of life. Carbon can make chains. Even if it triple binds something, you can still put another thing here. And if it's another carbon, I want to grow up to be like you. Anyways, so if you put another carbon here, then this carbon can bind with other things. Okay? And it starts to make chains. And so carbon has the ability to make really infinite chains. No matter how many bonds it's making, it can keep going as long as it's attaching to other carbons. Okay? And they can start making rings, and they start making little bent things. And the longer they get, okay, the more energy that gets stored in them. Because these covalent bonds store energy. There's energy stored in these bonds. When you break them, energy is released. When they form, energy is actually stored into the bond. Making a covalent bond is an endothermic process. Breaking a covalent bond is an exothermic process. Okay, so when we burn this, carbon chemicals tend to burn. When we burn them, we release the energy stored in the chemicals, and we release CO2 to the atmosphere, and we start, causing problems. But this is the cool thing with carbon bonding is that it can make double, triple, and single, double, and triple bonds with itself along with other things, and they can go on chains for forever. And they usually get capped off with hydrogens and stuff when they end their chains. But because of this, carbon is a fundamental part of our covalent bonding system. And I think we're going to stop there for today.